All right, let's go ahead and get started with our next talk. So we have Arun Debray, who will be telling us about stable diffeomorphism classifications of some unorientable four manifolds. So take it away, Arun.
Thank you. So first, I'd like to thank everyone for being here and showing up to my talk. And I'd also like to thank the organizers. I'm looking forward to the talks going on this week. So I'm going to talk about, as mentioned, stable diffeomorphism classification of some unorientable four manifolds. So four manifolds, this is a classification question in topology, not of up to diffeomorphism, which is really hard, but stable diffeomorphism, which is a little easier. And then so this is not the first time someone has proved a theorem like this. In fact, there are many of these, but most of them tend to say, okay, well, let's assume that our manifolds are oriented. And I decided not to do that. And so then, well, okay, what can you say? And then sometimes you can say something nice, and that's what I did. So first, I'm going to say what stable diffeomorphism is. This is some equivalence relation weaker than diffeomorphism. And I'll also tell you why I care. I am not really a four manifold topologist. So the question, I'd like to say something about the question that led me to this problem. So when you consider the stable diffeomorphism of four manifolds, there is one very large and powerful hammer. It is Kreck's modified surgery theory. So I'll tell you how it is wielded, and sort of, you can think of it as constructing a very good stable diffeomorphism invariant. And so I'll walk you through that classification, walk you through the construction of that invariant. And then I'll say, okay, the specific example that I calculated is it's a very special case. And well, what does the calculation look like in that case? So, okay, I said M is unorientable. Pi1 is order 2 mod 4, and in particular is finite. And there's one more assumption that we'll get into. So I have chat open, but it's on the side of my screen. And so it's possible, if you have questions and you ask them in chat and I see them, great. But if you ask and I don't see them, if someone could let me know, maybe you can unmute and ask your question. That would be helpful. Questions are great, and I hope that people have them. So four manifolds are hard to classify. This is this is sort of the remaining open case of the Poincare conjecture. And so we don't know if something looks kind of, or how should I say this? So classifying four manifolds up to diffeomorphism is too hard. And this is because you can reduce from that to the word problem for finitely generated groups. Basically, there are finitely generated groups which we cannot algorithmically decide whether they are the trivial group, and it's possible. And there are ways to construct, given a presentation of a group, you can construct a four manifold with that group as its fundamental group. And so we can't know whether, we can't decide whether those four manifolds are simply connected, and therefore we cannot classify four manifolds up to diffeomorphism. So so we would like to classify, diffeomorphism is sort of the eyes on the prize, but it's way too hard. You could also classify four manifolds up to homotopy equivalence, and this is I don't want to say too easy because it was hard work of many people, but it's solved. So due to I think combination of Donaldson and Friedman, it's understood what we can. I think it's using the it's understood what possibilities there are, and algebraic invariance to classify up to homotopy. So okay, we want something in the middle. It's not already solved. It's not impossibly hard. And so this is what stable diffeomorphism is. It's one of many different kinds of equivalence relationships you could put on four manifolds. And it's going to tell us that you can connect some on a bunch of copies of S2 cross S2, and then check for diffeomorphism. So M and N are stably diffeomorphic. If M connects a bunch of S2 cross S2s, is diffeomorphic to N connect these S2 cross S2s. We don't care what M and N are. So like I said, it's much easier than in general. And there's, we care about it for a reason, and I'll say what my particular reason is. And crucially, we're gonna work around the word problem, because stably diffeomorphic manifolds must have the same fundamental group. So what we're gonna do is we're gonna fix the fundamental group, or fix classes of fundamental groups, and then look at that classification. And this is how people traditionally study it. So what are some questions you might ask if you're studying stable diffeomorphism? So one thing you might say is, okay, let's fix a fundamental group. Are there, how many stable diffeomorphism classes of four manifolds are there? Are there finitely many? Can we write down representatives for these classes? And can we write down a complete set of stable diffeomorphism invariants? So that's sort of the dual one. So maybe we don't quite know what this is what's going to come up in practice for me at least, is we don't know what precisely the examples are because they come via some abstract construction. But we know that that these invariants will tell you if you have an example with this fundamental group, this is what it's you know which class it is in based on these 2 or 3 invariants. And finally, this one is, I'm not going to talk about this in my talk, but it's the kind of thing that people think about a lot, which is, can we bound the number of copies of S2 cross S2 that we need in the definition of stable diffeomorphism? So maybe if you say, pi1 is this particular group, then you only need 1 copy of S2 cross S2, and anything after that is redundant. So there are some results like this, usually proven by very different methods. So people are interested in stable diffeomorphism in its own accord, but I'll tell you why where I sort of became aware of this question. So I'm an algebraic topologist and I work on topological field theory. And I'm not going to tell you I'm not going to tell you about that because that's not the point of the talk. But what you can imagine is that a topological field theory, it's some complicated gadget. And in dimension 4, what it does is it produces 4 manifold invariants. So it's a machine that you put in you put in some defining stuff and you get out 4 manifold invariants. And the thing that makes it a topological field theory rather than just a 4 manifold invariant is saying that when you cut your manifolds up and put them and then glue them together, it behaves well under that procedure. So I'm happy to talk about that more later, but I'm going to leave this sort of vague motivation for now. So David Reuter has a paper from last year, which says, okay, what kinds of invariants can we obtain from 4D topological field theories? And so he put another axiom called semi-simplicity on his TFTs. And he showed that what you get out is always a stable diffeomorphism invariant. Semi-simple is, so anything that reasonably could come from physics. Topological field theories have something to do with physics. I'm not going to say much more about that. But anything that reasonably comes from physics is unitary and is extended. And therefore, those are 2 different reasons that it's semi-simple. So Gomf has a theorem that stable diffeomorphism invariants cannot detect exotic smooth structures. So if you were interested in using topological field theories to detect exotic, say exotic spheres maybe is the big one, but other exotic 4 manifolds, you're now out of luck. Well, okay, all of this story, this whole slide, we've put orientations on our manifolds. Gomf's theorem, Reuter's result. And so there's a notion of an unoriented topological field theory, and you just get invariants of unoriented 4 manifolds. And so it turns out that these can see exotic smooth structures on RP4. So there's a paper of Tada, Kobayashi, Bomash, and Barkeshli. I'd like to point out this is a physics paper that is still asking about 4 manifold invariants. And it's sort of these kinds of questions that led me to thinking about unoriented stable diffeomorphism. Before I state the main theorem, are there any questions? Okay. So let's say I have a fundamental group of an unorientable manifold. So given a loop, you can therefore say whether it is orientation preserving or orientation reversing, right? You walk around the loop and you ask, are left and right the same thing as when I started? And it's in dimension 4, you've got a little more to say than that, but this gives you a surjection onto Z mod 2. Because it's unorientable, there is an orientation reversing loop. And then, when you compose 2 orientation reversing loops, you get back to orientation preserving. And so K is the kernel, so we get a short exact sequence. So what I'm going to do is put 2 assumptions in. First, G is finite of order 2 mod 4. And second, and this assumption is quite strong, but it turns out to be necessary. If you have an extension, then the quotient acts on the subgroup as by some automorphisms. And then when we take homology, group homology in this case, there's an induced action on that. So what I'd like to say is I'd like the quotient Z mod 2 to act trivially on the homology of the kernel K. You can weaken this a little bit in practice, but and in fact, like I said, this is quite strong. It rules out, for example, dihedral groups, which are sort of the first example of these extensions you might see. But with these assumptions in place, we can classify unorientable 4 manifolds with this fundamental group up to stable diffeomorphism. So the classification falls into 3 pieces. So I'm not going to tell you exactly what pin plus and pin minus structures are, but these are unorientable analogs of spin structures. So for an oriented manifold, you could ask whether it admits a spin structure. So for example, all closed oriented surfaces do, but CP2 does not. And so there are two versions of this that are unorientable. One is called pin plus, one is called pin minus. And so the classification falls into three different parts. You could say, okay, well, let's look at the cases where it's pin plus, let's look at the cases where it's pin minus, and let's look at the cases where it admits neither structure. And what you end up learning is that there are 9 classes where it's pin plus, 1 where it's pin minus, and 4 which it's neither. So it's interesting. I also figured out what the invariants are, so that's something I can talk about later. And also, I'm not going to say too much about this in this talk, but you can run the same story for stable homeomorphism of topological form manifolds, where you connect some on copy S2 cross S2 and only ask for a homeomorphism. And roughly the same, you can tell the same story, but in the end, the actual computations you do are different. There's notions of topological pin structures, and so you get 10 which are topologically pin plus, 2 which are topologically pin minus, and 8 which are neither. So this is the theorem. Next, unless there are questions that people want to address right now, next I'm going to dive into how you prove this. So the next couple slides are, what previously happened was nice and geometric topology, which is good because this is this is more of a geometric topology conference. But the tool that we need to classify this is a little more algebra topological. So I'm just going to go through how to build the stable diffeomorphism invariant that allows the proof of those classification theorems. So the infinite stable orthogonal group, you can sort of take the inclusion, of ON inside ON plus 1, inside ON plus 2, etc. And that's this topological group called O, and we take its classifying space. So this is a topological space and, such that homotopy classes of maps to it are in one-to-one correspondence with isomorphism classes of virtual stable vector bundles. So virtual means we take differences of vector bundles formally, sort of like integers are formal differences of natural numbers. And stable is saying that, I sort of take off my glasses and don't notice the difference between a vector bundle and a vector bundle plus a trivial summand, which I think is here, even though I'm not wearing my glasses, I can't be sure. Good. So we're classifying virtual vector bundles, sort of introducing more data, and then stable, meaning quotienting out by an equivalence relation. And that's what maps to BO tell us. So BO is defined in a somewhat abstract way, but its homotopy type is uniquely defined. So the tangent bundle on a manifold canonically gives us a map to BO, but we're going to care about another one called the stable normal bundle. And so the idea is that Whitney and Wu proved that the isotopy class of an embedding inside a very high dimensional sphere is unique. So Whitney gets us into Sn, and then Wu says, puff up n by another couple by like maybe 2, and then there's no isotopy classes. Knots all unknown. And so the normal bundle for this embedding is defined up to isomorphism. So finally, we had to choose n, and that's not great. So if you increase n, you're adding on trivial summands to the normal bundle, just like the normal bundle for Sn inside Sn plus 1. So the stable equivalence class of this vector bundle is defined, and therefore we get a homotopy class of maps to BO. So from this, we're going to build a stable diffeomorphism invariant, which captures key information about the universal cover. It knows pi1, and it knows the first 2 Stiefel-Whitney classes, as well as whether the universal cover of your manifold is spin. So this invariant's a little bit weird. It's formulated as a symmetry type. It's the data you need to define bordism groups. So for example, one symmetry type is oriented. Another symmetry type is pin plus with a principal Z3 bundle. Things such that when you take that data, you can induce that data on a boundary and therefore define notions of bordism and therefore bordism groups. Oh, sorry. If you're used to calling this cobordism, I will use the words interchangeably. So a symmetry type is defined as a space and a fibration to this stable orthogonal group classifying space BO. And so the idea is you can make sense of, for example, psi structures. So you have the stable normal bundle, and you're saying actually the map that classifies it lifts to B. So a key example, the one that sort of the general case is based on, is orientations. So you can analogously to BO, you can define BSO, and a lift across this is saying, well, what this amounts to is saying your partition functions, or sorry, your transition functions, my bad, for the normal bundle, they're valued in ON, but really you've chosen how to put them inside SON. You've chosen charts and transition functions that make that work. And that's providing the data of a lift here when B is BSO. So for example, you could get an orientation, and if you use B spin instead of BSO, you get a spin structure. So the normal one type is defined in a Postnikov way. You use it. So we want the map nu to be 2 connected, meaning that it knows pi0 and pi1 of M. And we want psi to be 2 co-connected, meaning in some sense it knows everything else about BO. So when I said D with an asterisk, Postnikov theory is telling you the homotopy type of the space B in this map to BO, but it's not telling you a homeomorphism type. This is going to be okay. We just care about the normal one type as a homotopy type. And so to reiterate this, so Postnikov theory guarantees this exists and is uniquely defined up to homotopy. And the normal one type is saying, I want to know the low dimensional homotopical information about it. And then after that, I use BO. So why is this? So I claim that the normal one type is a stable diffeomorphism invariant. And the idea is that S2 cross S2, pi0 and pi1 are completely trivial. And pi2 is only scarcely more interesting. And so if you work out what is the normal one type of S2 cross S2, it's sort of the trivial one. What's it called? Not the connected double cover, but maybe the 2 connected cover. And so the upshot is, the upshot is that M and M connect sum S2 cross S2 have the same normal one type. So that is a stable diffeomorphism invariant. We're going to make it better. Since I only have a few minutes left, I'm going to wait for questions until the end, unless it's something like urgent, in which case, let me know. But we're going to upgrade this stable diffeomorphism invariant. So we have the normal one type of M, and also of M connect sum S2 cross S2. Now we're going to introduce bordism. So in general, so S2 cross S2 bounds S2 cross a disk. So you can sort of fill in this thing. And so stably diffeomorphic manifolds are borded. Bordism is a very weak equivalence relation on 4 manifolds. So we'd like to upgrade this. What is in fact true is that S2 cross S2 bounds as a psi manifold. And in fact, M and M connect sum S2 cross S2. You can choose psi structures on them, which are bordant as psi structures. So that is, you're not just saying that these two are the common boundary of a 5 manifold that's compact, but also you've chosen the psi structure, the kind that was picked out by this normal one type, which respects that boundary decomposition. So this can be much stronger. So the set of equivalence classes of psi structures is an abelian group under disjoint union. We're going to call it omega fork psi. And so we're going to build, so the stable diffeomorphism invariant sends M to its class here. Now, that's not quite right. So what we're going to do, because we had to choose a psi structure. So what we're going to do is we're going to say, okay, inside this set, omega fork psi, we're going to quotient out by saying, okay, anytime that 2 different psi structures have to give you 2 different classes here, we're going to identify them. And so now you have some set which could be much smaller, and so in fact, but just by the way we've built it, the image of M in that set is a stable diffeomorphism invariant. So this is a little bit fancier, at least. Now let's see how good it is. So okay, I said the bordism group mod equivalence. Matthias Kreck proved that this is a complete stable diffeomorphism invariant for manifolds with the same normal one type. So this sees everything, which is kind of, when I read this, I was not expecting this. And moreover, every element of this bordism group is realized. Or I guess, so every element of the set of stable diffeomorphism classes is this bordism group mod the equivalence relation. And so how do you actually make these computations, which I'll tell you a little bit in the last minute, is that you proceed just like you do for, you just compute the bordism groups and then compute the equivalence relations. And you do this one normal one type at a time. So in the last minute, I'll tell you the proof sketch, the main theorem. So basically, the hypothesis that G is 2 mod 4 allows you to map to a much simpler symmetry type, where you say, G is complicated. Let's just look at Z mod 2. And the hypothesis that Z2 acts trivial on the cohomology of K says that the bordism groups are the same. So this is just an algebraic topology argument where you say, okay, well, I have control over this, this entry in this spectral sequence, and therefore the map is the same. And so now I need to know psi prime bordism. Sorry, I'll finish up soon. And so you can interpret psi prime bordism as twisted spin bordism or twisted oriented bordism. But in particular, it's known what these things are, in that they give you either unoriented four-dimensional bordism or pin plus or pin minus bordism. And these things are known. Renee Tom did unoriented, Kirby Taylor did pin plus and pin minus. And so what you can actually do is you can just look them up and then use that to compute this equivalence relation, and then use that to obtain the stable diffeomorphism classification. So there's no unorientable spin manifolds. One case is totally non-spin. So in this case, psi prime is unoriented manifolds. And so you get Z2 plus Z2 with projective space and product projective spaces as generators. And so when I said oxi x trivially, I should have said the equivalence relation is the trivial equivalence relation, meaning there are 4 classes. There are 2 remaining options. One is in which you fix the characteristic classes. So the normal one type fixes W2 as W1 squared. So now you get pin minus bordism. But fourth pin minus bordism vanishes. So there's only the one class. All such 4 manifolds are stably diffeomorphic, with the fundamental group fixed. And the last one, this one is more interesting, is if you say, I just want W2 equals 0 and no condition on W1. So this gives you the fourth pin plus bordism. This is Z mod 16 and is generated by RP4. So shown by Vince Giambovo and Kirby Taylor. And now the equivalence relation is now interesting. The 2 pin plus structures on RP4 represent +1 and -1. So we need to quotient out by the relation x is minus x, and we get the 9 classes 0 through 8. And that's the proof of the theorem. So sorry for going over time. Thank you for listening.
Let's thank our speaker. Wonderful. Are there any questions? You can unmute yourself, put it in the chat, whatever you feel most comfortable.
I have a quick question.
Okay.
Can you hear me?
Yes.
Can you say something about, for a total beginner like me, why S2 cross S2 in the definition of stable diffeomorphism? Like, could you have chosen a different simply connected 4 manifold?
So you could choose. So I mean, the notion of stable diffeomorphism, like you don't even need simple connectivity. Yeah, I really like this question. So there's various work that says, okay, for if you replace this with your favorite 4 manifold that is not S2 cross S2, what can you say? So I think Peter Teichner and some collaborators, I hope I have the right list of names, but they did this for CP2, and so they obtained a different algebraic classification question, not bordism, but something else. For me, it was sort of a reverse engineering. Like I care about TFT and I care about bordism. So, and S2 cross S2 appears there. But if you wanted to say, okay, well, what happens if I used RP4? I mean, I think that would be cool. I don't know if anyone's thought about that one.
Thanks.
Yeah, great question.